Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we were discussing about the convolution integral, and we started with the graphical approach of calculation of the convolution integral. So, we will continue our discussion from yesterday's class. Let us recap what we discussed about the convolution integral. We discussed that convolution is nothing but folding. Folding means we take the mirror image of one of the function which will be part of the convolution integral, and then convolution of two functions is achieved through the convolution integral, which is defined as yt is equal to minus infinity to infinity integral f1 lambda f2 t minus lambda d lambda. So, this is what we discussed about the convolution integral, and then we stabilize that the convolution of f1 and f2 is represented as the f1 in then the asterisk sign and f2. So, this asterisk defines that these two functions are having convolution and the output is yt. Now, we also stabilize that the Laplace transform of convolution of f1 and f2 can be computed by simply multiplying the respective Laplace transforms of the functions f1 and f2. So, we said that f1s into f2s is nothing but Laplace of the convolution of f1 and f2. So, which means that the convolution in time domain is equivalent to multiplication in S domain. Now, we started our discussion on graphical approach of evaluating the convolution integral, and we said that the graphical procedure for evaluating the convolution integral usually involves 4 steps. What were those 4 steps? First was folding. That means we take the mirror image of one function, say h lambda in this case, about the ordinate axis. So, then we will get function called h minus lambda. Then second step is displacement, where we shift or delay the h minus lambda by t, so that we get the function h t minus lambda. Third is multiplication, means we find the product of h t minus lambda and another function x lambda, and then we finally get the integration. For a given time t, we calculate the area under the product h t minus lambda and x lambda for lambda ranging between 0 to t, and then we get the convolution of functions h and x. Now, this particular approach let us try to understand with the help of one example. Let us say that we have two functions, one is x1 t, which is as shown in the figure, and x2 t is also as shown in the figure. What we have to do? We have to find the convolution of two signals, that is x1 and x2. So, the 4 steps which we discussed, we will follow them and try to find out the convolution of x1 and x2. So, as part of our first step to carry out the convolution, we first fold x1 t. So, we will see when we fold how it will look like, and then we will shift by t, and finally, for different value of t we will now multiply the two functions and then integrate to determine the area of overlapping regions. So, what we will do? We will first take the mirror image. So, the mirror image of x1 t will be like as shown in the figure. So, now it will become x minus lambda, you will take the lambda as an axis. So, now instead of having shape like this, it has become the mirror image. Now the shape is like this, and then we will shift the function by t. So now if you shift it by t, it will shift in the lambda axis, and it will range now between t minus 1 to t. So instead of minus 1 to 0, which was there in the mirror image, now it is having the range between t minus 1 to t. Now if you start moving this particular function, that is x1 t minus lambda, and you shift over x2 lambda, because here it will become now x2 lambda. So we will put both of these signals on the same axis. So what will happen, you will start now shifting this integral with respect to the various values of t, and then we will find out what would be the integral in the cases of different values of t. So first we will take that, let us see that the t is ranging between 0 to 1. So when t ranges between 0 to 1, the maximum value of t will be 1 in this case. So when you have 1 coming at this point, it means that there will be no overlap between these two functions. So what we can say? We can say the convolution of x1 and x2 for time t between 0 to 1 is 0. So this is what we got for the time between 0 to 1. Next, let us see that the now the time is ranging between 1 to 2. So what will happen now? The two signals will overlap between 1 to t. So if you are shifting this function, which was earlier here, further, then you will see that for some time, that is between 1 to t, this function will overlap, right. So what you can do now? You can find the convolution of these two functions by using convolution integral. So for this particular time between 1 to t, the integral will be between 1 to t, and the values would be 2 multiplied by 1, because it is 2 and it is 1. So when you solve, you will get the value of yt as 2 into t minus 1, when the t is ranging between 1 to 2. Now we will shift this signal further in this direction, then we will try to find out the value of the convolution of two signals for time between 2 to 3. So when you will see that the time is ranging between 2 to 3, two signals are completely overlapping, and the overlap is completely between t minus 1 to t, because the function x1 t minus lambda ranges between t minus 1 to t. So what will happen, that it will completely overlap the x2 lambda function. So what we can do? We can now find the value of yt, that would be ranging between t minus 1 to t. The values would be now 2 and 1 for the these two functions. So finally we get the value as 2. So we can say the convolution of two functions, two signals between 2 time 2 to 3 is 2. Now third case, when the time t is ranging between 3 to 4, means the sum portion of this function x1 t minus lambda would be overlapping between x2 and x1, and what would be the overlap period? These signals would be overlapping between t minus 1 to 3. So these would be the two limits on which your signal will overlap. So now for yt, this the integral will be ranging between t minus 1 to 3, and when we will solve, we will get the value of yt as 8 minus 2t for time t ranging between 3 to 4. Now for time t greater than 4, you will see that now the signal are not overlapping. So what we can say, that yt will be 0 for time t greater than is 4. Now, if you combine all the equations, we can say that the convolution of x 1 and x 2 is 0 for t between 0 to 1, 2t minus 2 for time t between 1 to 2, 2 for time between 2 to 3, 8 minus 2t for time t ranging between 3 to 4, and again 0 for t greater than 4. Now, if you plot, what you will get? You will get that up to 1 it is 0, and then it is incrementing because it is a 2t minus 2, then it is a constant with maximum value of 2, and then again decreasing with value 8 minus 2t, and then finally 0. So, this function which you have now got y t is the convolution of two functions x 1 and x 2 which were defined in the example. Now, the next question would be how you will utilize the convolution integral in circuit analysis. So, let us see with another example that how you will utilize the convolution integral in solving the circuits. So, let us take one RL circuit which is shown in the figure below. We will use the convolution integral to find the response I naught at any time t due to the excitation shown in the figure. So, now this is the excitation which is applied at t is equal to 0 with value 1, and it becomes 0 at time t is equal to 2. So, now to solve this problem we have to first use the technique which we discussed, that we will first find the unit impulse response, that is ST of the circuit. So, when we use the unit impulse response, what we have to do? We will apply the current division principle in S domain and find the value of I naught. So, let us first convert this circuit into S domain. So, when you convert into S domain, the current source will become Is, resistance will remain same, and the value of inductor, that is 1 Henry, will become S in this case, and the current is I naught. Now, we have to find out the transfer function of this particular circuit, that is I naught by Is. So, first let us try to find out the value of I naught. I naught is nothing but if you use the current division here. So, when you use current division, the value of I naught is nothing but 1 upon S plus 1 into Is. So, this you will get with the help of current division. Then you find out the transfer function Hs, that is nothing but I naught upon Is. So, you will get simply the transfer function of the circuit, which is Hs. Now, if you take the inverse Laplace transform of Hs, what you get? That you get Ht is equal to e to the power minus t ut. So, that is simply by using frequency shift property, you can find out the value of Ht, that is equal to e to the power minus t ut. And what is this? This is basically the impulse response of the circuit. Now, let us see the current source which is given. This current source can be represented as Is at any time t is equal to ut minus u t minus 2. How? So, what will be ut? Ut would be like this, and ut minus 2 with negative sign would be like this. So, what will happen? Only for this period the Is will be 1, otherwise it will be 0. So, when you convert Is into two unit step functions, you will represent it like ut minus u t minus 2, because it is delayed by 2 seconds. Now, you have Is, you have got the impulse response of the circuit. What we have to do? We have to find the value of I naught at any time t with the help of convolution integral. So, what we will do now? We will take the convolution of Is and H functions. So, what we can write? We can write 0 to t is, we will take the dummy variable as lambda. So, is lambda h t minus lambda d lambda. So, we will put the value of is, that is u lambda minus 2, that is the value of is which we calculated. So, then we multiply by e to the power minus t minus lambda d lambda, that is again the value which we computed. So, we have now the convolution integral ready to be solved. Now, here if you see this particular integral, you can divide this integral into two parts. For time t ranging between 0 to 2, this particular value will be 0, because it will be 1 when t is greater than 2. So, for time t ranging between 0 to 2, this will be 0. So, finally, we are left with only this which will become 1 and e to the power minus t minus lambda, because this the u lambda is 1 for t greater than 0. So, when you will solve, you will get the value of this I naught t between time t 0 to 2 as 1 minus e to the power minus t ampere. Now, for time t greater than 2, this will anyway remain there. So, when you separate these two terms, you can simply say that 0 to t u lambda e to the power minus t lambda d lambda is nothing but what we calculated in the previous step. So, you can simply put the value as 1 minus e to the power minus t, and then next is u lambda minus 2 function. Now, we know that this will have value as 1 when the time t is ranging between 2 to t. So, we will change the integral value from 2 to t, this value will become 1 and then e to the power minus t minus lambda d lambda. Now, if you solve this and simplify, you will get the value of this particular current, that is I at time t greater than 2 is e to the power minus t into e square minus 1 ampere. So, if you now see these two values for time t ranging between 0 to 2, this is 1 minus e to the power minus t ampere. So, at this point the current is exponentially rising. So, if you are asked to plot the I naught t also on this particular signal. So, for time t ranging between 0 to 2, it is exponentially rising. So, your response would be like this, and for t greater than 2, this term is anyway constant. So, the response would be governed by e to the power minus t, means for t greater than 2, it will be exponentially decaying. So, the I naught t for time t greater than 2 would be exponentially decaying. So, this would be the response of current I naught for the input signal applied as Is. So, now you can understand how you can solve the circuits with the help of convolution integral. Now, let us move on to another concept called network stability. Here the circuit is stable if its impulse response is bounded, means the Ht converges to a finite value when t tends to infinity, and if it is unstable if St grows without bound as t tends to infinity. So, in mathematical terms, you can say that the circuit is stable when limit t tends to infinity, the value of Ht is finite. Now, since the transfer function Hs is the Laplace transform of the impulse response Ht, this is what we discussed. So, Hs must meet the certain requirement in order for this particular equation to hold. So, we know that the transfer function of the circuit can be written as Ns by ds, that is numerator and denominator, and let us see what is the criteria for this Hs to follow the stability criteria. So, first is that where roots of Ns equal to 0, then those are called zeros, because this makes Hs equal to 0, while the roots of d, that is denominator, if you make the denominator equal to 0, then what the roots you get are called poles of Hs, because they cause H tends to infinity when you put the values of poles. Now, zeros and poles of Hs are often located in the S plane as shown in the figure. So, generally the poles would be in the left half plane and zeros can be at any location, whether here or maybe at the imaginary axis. Now, Hs can be written in the form of, in the terms of its number of poles. Suppose there are n number of poles. So, what you can write, numerator will remain there, but denominator you can separate out in the form of like S plus P1, S plus P2 if there are n number of poles. So, you can represent the denominator like this. Now, what are the criteria? So, there are two basic requirements for the circuit to be stable. First is that degree of Ns, that is numerator, must be less than the degree of denominator. If it is not, then what will happen? If you represent Hs, like if you have the degree of numerator is more than denominator, you can represent Hs as some values kn s to the power n and the exponentials, and this would be like one expression for those values which are like if the degree of numerator is more than degree of denominator, plus some residual where the degree of residual is less than denominator. So, when you divide ds by ns and you simplify, you can represent Hs as some expression plus some residual divided by denominator. Now, if you see this particular expression where r is degree of r is less than degree of d. So, this will anyway be stable when t tends to infinity, but if you see this particular segment, this segment will cause the Hs tends to infinity when you put value of s tends to infinity. Because of this, the Hs will be unstable. So, the first requirement is that this for system to be stable, the Ns should be less than the degree of Ns should be less than the degree of ds. So, when you take the inverse of the Hs, the inverse of Hs will not meet the stability condition. The stability condition what we discussed was limit t tends to infinity, St should be finite. So, when you have S in the numerator as an independent quantity in Hs, this will not allow Hs to be finite, the inverse Laplace of Hs to be finite when t tends to infinity. So, that is why your Ns, so the degree of Ns should be less than the degree of ds. Now, the second condition is that all poles of Hs, that is all roots of the denominator equation, that is ds equal to 0, must have negative real parts. That means that all poles must lie in the left half of the S plane. If you see the S plane, the poles must lie in the left half only. Okay. So, these are the two conditions which we have to follow as a requirement for Hs to of the circuit to be stable. Now, as we know that we can represent Hs in the form of this, or you can represent as a K1 upon S plus P1 plus K2 upon S plus P2 and so on. So, what you can write, if you take the inverse Laplace transform of Hs, you can simply write Ht is nothing but K1 e to the power minus P1 t plus K2 into e to the power minus P2 t and so on. Now, if you observe this particular equation, you will see that the value of P, that is P1 to Pn, must be positive, which will make the pole, that is S is equal to minus Pi in the left half plane. So, what does it mean? Then you will see that if this is positive, this particular expression will be e to the power minus P1 t, which would be exponentially decaying, which makes sure that the Ht is bounded, means it is converging to a particular value with the increase in time t. Now, in unstable circuit, it will never reach to its steady state value, because the transient response does not decay to 0. So, if P is negative instead of P being positive, this term will become e to the power, say some positive term lambda, e to the power lambda t. So, when you see this exponentially rising term, then the expression, that is Ht equal to the K1 e to the power minus P1 t, this will become K1 e to the power lambda 1 t, K2 e to the power lambda 2 t and so on, where lambda 1 lambda 2 are the positive terms. Then what will happen? This will never reach to its steady state value, because e to the power lambda t is always rising, it is not exponentially decaying, it is exponentially rising. So, in that case transient response will not decay to 0. So, the steady state analysis is only applicable to the stable circuits. Now, let us see how we can correlate with our electrical circuits. Now, if the circuit is made up of passive elements, that is R, L and C, and independent sources are part of the circuit, the system cannot be stable, cannot be unstable, because this, if it is unstable, then it would imply that some branch current or voltage would grow indefinitely when sources are set to 0, which does not happen practically in the circuits which are having R, L and C component, because R is the component which is responsible to decay the response. So, the passive elements cannot generate such indefinite growth. So, passive circuits either are stable or have poles with 0 real parts. So, what does it mean? We will discuss when we will see this particular example. Let us see this particular case. If you have a series RLC circuit, the transfer function of series RLC circuit can be given as Hs is equal to V naught by Vs. So, if you compile the ratio between V naught and Vs, you will see one expression in the denominator, that is S square plus Sr by L plus 1 upon Lc. So, this expression we have already seen when we were discussing about the source free as well as step response of the series RLC circuit. So, the denominator expression would be S square plus S R by L plus 1 by Lc equal to 0. Now, this is same as the characteristic equation which we obtained in case of series RLC circuit. So, what we can say now? We can say that this particular circuit will have two poles, and the value would be minus alpha plus minus root of alpha square minus omega naught square, where alpha is R upon 2L and omega naught is 1 upon root LC, and this we have already seen when we were discussing the series RLC circuit. So, now if you see this particular expression for R, L and C greater than 0, two poles will always lie in the left half of S plane. This implies that the circuit is always stable. However, when you see R is equal to 0, that is alpha is equal to 0, the circuit becomes oscillatory. Although ideally it is possible, but it does not happen practically because R will never be 0. So, this case when you have alpha is equal to 0, this particular condition will apply. The passive circuits will have poles with 0 real parts. So, when you have poles lying on the imaginary axis, then you will see the real part is 0 and the response would be oscillatory. So, with this we can close our today's session, and we will continue our discussion on this particular aspect in the next session also. Thank you.